Okay, so today we're going to talk about how to do a t-test in R&R Studio using this function called Inference. So a t-test is basically comparing two samples and looking at, to see if the means of those two samples are, statistically different. Okay, and for example, let's say you have maybe two brands of car tires, brand A, brand B. And you want to test, let's say, to see if the wear after so many months, maybe higher or lower for a certain brand. Okay, so you could use a t-test for something like that. And, there's a lot of things you could use it for, but I've actually generated a data set here that has two levels, factor A and factor B, two categorical levels, and some measurement. Okay, and I know this measurement comes from an independent data source, so that means that the data is independent, which means that each data point is independent of any other data point. And I know it comes from a distribution with a finite mean and variance. Okay. And in this particular set, I also know it comes from a normal distribution. So the normal distribution is great if you're doing parametric type testing, and it's something that's definitely valuable to have. So we want to test and see if the mean of this factor group A is different than this factor or group B. Well, one of the first things I like to do is actually plot the data. So I'm going to install or load ggplot. So ggplot is a great graphics tool for R&R Studio. And if you don't have it in your R Studio here, you can just go to Tools, Install Packages, and simply type it in. You'll find it there. You can install it that way. The other one we're going to use is called library Statsr. Okay, so this is a library that actually came from a course that I took a while back in Coursera that has a great function called Inference for doing these types of t-tests. And if you're curious, where to find it, you can actually find this one on GitHub. Just type a question mark in front of it, and you'll see that there's the address for it and where you can find it for more information. So it has this, function called Inference. And the way it works is this way. So this is interesting. So here we start typing it, and it'll tell you all the different things that you can, add to this function. Okay, so you can configure it. And let's go ahead and do a function F1 for additional help, and it actually shows you what all the different parameters or arguments you can pass to this function. So we're going to do an inference, and first thing we do is actually before we do that, let's go ahead and plot the data. And we'll do data set. That's the name of our data. Add an aesthetic. X equals the factor. Y equals the measurement. Should always graph your data first. Gives you a lot of good insight. And there it is. So there is what the box plots look for each of the two samples. Okay. So it definitely looks like factor B here is definitely higher than factor A. The variability is about the same. For a t-test, it's nice to have equal variance. Okay, it simplifies a lot of other things. And we can actually plot the data points on here too. So let's go ahead and up arrow key, point. And then we simply added the data values on top as points. Okay. So now let's go to inference. And its data set is our data. And we're going to say x equals a factor. Y equals the measurement. Okay. Statistic is going to equal to the mean. So that's we're testing between the mean. Okay, so here you can say parameter estimate. You can do a mean, a median, or proportion. And let's see what else we need to do here. Type equals HT. So type over here is it's going to either be a confidence interval approach or a hypothesis test. The hypothesis test. The null is assumed to be 0 or no difference. And the alternative is going to be two-sided. So you can also choose, less, greater, or two-sided. Typically in these tests we always choose the two-sided option. And the method is theoretical. So you can use theoretical, which is based on the central limit theorem, or some simulation approach. And there's some other things here as well you can add on if you need to as well. Hit enter, and there it is. So here's our t-test. We have two levels, which is factor A and B. For factor A, we had 20 data values. We had a y bar of minus 0.1905, a standard deviation of 1.0259. And for the second data set, you can see 20 data points, y bar of 0.8665, and a standard deviation of 0.8627. The null hypothesis, saying mu of A equals mu of B, and the alternative says that mu of A does not equal mu of B. Our t-value here was minus 3.5265 on 19 degrees of freedom, and that gives us a p-value of 0.023. And if you're using the traditional 0.05 or even 0.01 cutoff, this would indicate some kind of statistical significance here. Now, here, this is also kind of a neat feature. So one of the things, in addition to this output here, is we actually can see, let's actually expand this. We'll copy the clipboard, make it a little bit wider. And we can actually see the distribution of, factor A here, and then factor B. Factor B definitely seems a little bit greater than factor A. We saw that in the box plots as well. And this is probably one of the coolest features of this inference function. This is the null distribution. Okay, so this is the difference between factor, A and factor B, given that the null hypothesis is true. So you can see that this difference, that we observed in these two data sets here, is pretty far down in these tails, okay, and that's also indicated by this p-value as well. So again, it's saying that this observed difference is pretty uncommon if the null hypothesis is true. So we definitely could reject the null hypothesis here and have confidence in the alternative that these two are different. Anyway, that's how the inference function works in our studio here. I just think this is a really nifty way to approach the t-test, and definitely hope you can use this and hope it helps. Thanks, and we'll talk to you again.